Hi, myself Dr. S.K. Bushra. This is a video lecture in physics for class 12 students, and the topic is electrostatics. Lesson 1 of chapter 2, Electric Potential, part 1. The themes of discussion of this lesson will be the background of the potential formulation, to be followed by the definition of electric potential, and then electric potential due to a point charge, and finally superposition principle for electric potential. So let's begin. The background. The electric field E is a special kind of a vector. Its three components are not mutually independent. That is, this feature of E allows it to be expressed as a space rate of change of a certain scalar quantity. The scalar quantity turns out to be the work done in displacing a unit positive charge in an electric field. In due course of time, this scalar quantity was named as the electric potential. The electric potential describes an electric field just as elegantly as by the electric field E. Now the question is, how come a scalar, one component, could possibly contain all the information carried by a vector, three components? We have already seen that the three components of E are not mutually independent. The answer to the question is this particular property of E. But we are more than happy to describe an electric field in terms of potential because it is a scalar formulation. A scalar formulation makes the description much simpler. If need be, one can easily switch over from potential to field formulation and vice versa. Now, work done in an electric field. The force experienced by a charge Q in an electric field is given by F subscript E equal to Q into E, where E is the electric field at the location of the charge. If Fe displaces the charge, then the work is done by the field. If, on the other hand, an external agent displaces the charge against the incumbent force Fe, then the work is said to be done by the external agent. One adjusts the external force to be equal and opposite to the incumbent electric force so that the charge does not gain any kinetic energy during the process, or in other words, does not suffer an acceleration. The work done is path independent and depends only on the initial and final positions of the charge in the electric field. A charge Q is being transferred from locations A to B in an electric field. Irrespective of the path of travel, either path 1 or path 2 or path 3, for example, the work done will be the same. Definition of electric potential. We begin with the definition of electric potential difference. The electric potential difference between 2 points in an electric field is the amount of work done by an external force in transferring a unit positive charge from one point to the other without causing any acceleration to the charge in the process. Let A and B be 2 points in an electric field. The electric potential difference across A and B is defined as work done WAB divided by Q0. Here, WAB is the amount of work done in transferring a test charge Q0 from A to B by an external force without causing an acceleration to the charge. Thus, the electric potential difference across 2 points in an electric field is the amount of work done in transferring a unit positive charge from one point to the other by an external force without causing an acceleration to the charge. The definition invokes a test charge so that the incumbent electric field is not distorted by a memoed charge like the unit positive charge. Now we set the zero of the potential at infinity. Since V at infinity is equal to 0, this reference point is equivalent to selecting a place where V is equal to 0. Suppose the point A is located at infinity. Then we have potential at B minus potential at infinity equal to W infinity to B divided by Q naught. Simplifies to finally potential at B equal to W infinity to B divided by Q naught. Thus, the electric potential at a point in an electric field is the amount of work done by an external force in transferring a unit positive charge from infinity to that point without causing an acceleration to the charge. Remarks. We can appreciate the role played by the path independence of the work done in an electric field in defining the potential function. Without it, the definition of V would have been useless, since altering the path would have changed its value. While defining the potential, the reference point was selected in a logical but arbitrary fashion. This makes the definition of potential somewhat ambiguous. However, the electric potential difference across 2 points is free from this ambiguity. Suppose V dash A and V dash B have been defined with respect to a different reference point, say K. Then V at B is equal to W infinity B divided by Q naught. Now, the term W infinity to B can be expressed as summation of W infinity to K and W K to B. As K is a fixed point, W infinity to K divided by Q naught is a constant. Let it be alpha. Therefore, we can express VB as alpha plus V dash B. Similarly, VA is equal to alpha plus V dash A. Now, V at B minus V at A is equal to alpha plus V dash B minus alpha minus V dash A equal to V dash B minus V dash A. Thus, the potential difference is free from the ambiguity inherent in the definition of electric potential. We'll later see that it is not the absolute value of the potential, but a potential difference, in fact the gradient of potential, which is physically significant. It is obvious from its definition in terms of work done that the electric potential is a scalar quantity. The unit of electric potential is joule per coulomb, or more popularly, volt. Now, electric potential due to a point charge. In the figure, P is a point in the neighborhood of a point charge Q at a distance r from it. A test charge Q naught is being brought from infinity to the point P by an external agent. As work done in displacing a charge in an electric field is path independent, we select a radial line as the path of travel of the test charge, ostensibly to simplify the calculations. P dash is an intermediate position of the test charge during its journey at a distance rds from the point charge q. The electric field of q at p dash is as given by equation 1. Clearly, E points radially out. The force on the testers is therefore F equal to Q naught into E. The rest is as given in equation 2. Without causing any acceleration, the testers is displaced through an infinitesimal extent dr dash towards the point charge Q. This is affected by an external force F subscript ext, which is equal and opposite to F. Regarding the asterisks, E and hence F may be assumed to be a constant within an infinitesimal, that is vanishingly small interval dr dash in displacement. Work done during the process is therefore dw equal to F dot dr dash equal to minus F subscript ext dot dr dash. This is equation 3. Then the net work done by the external agent in transferring the tester's Q naught from infinity to P is W equal to integration infinity to P dW equal to minus integration infinity to P F subscript ext dot dr dash. This is equation 4. Since F subscript ext and dr dash are in the same direction, we have W equal to minus integration infinity to P F ext multiplied by dr dash. This is a simple multiplication. This is equation 5. Regarding the asterisks, the compulsion of carrying out the integration is being explained shortly. Substituting for F ext, work done W is equal to, as in the equation, bringing the constant out of the integral, we have this. The integration of 1 by r dash square is equal to minus 1 by r dash. We substitute the limits. Then finally we get W equal to 1 by 4 pi epsilon naught Q into Q naught divided by R. This is equation 6. Therefore, by definition, the electric potential at P is W by Q naught is equal to 1 by 4 pi epsilon naught Q by R. This is equation 7. Coming back to the asterisks, why do we have to carry out the integration here? In this particular case, and in fact, more often than not, the incumbent electric field is non-uniform and hence force on a charge changes with position in the field. So during a non-accelerated finite displacement of a charge in an electric field, the external force needs to be adjusted continually, which renders the usual formula for work done, F dot delta x, where F and delta x respectively denote the force and the total displacement, inoperable. In order to start the issue, we divide the travel path of the charge into innumerable infinitesimal length elements within which the field remains effectively constant. Therefore, the work done during an infinitesimal displacement may be calculated by using the formula F dot dx, where dx denotes an infinitesimal displacement and F is the force in that element of the displacement. Then we may obtain the total work done by summing the works done during all the infinitesimal displacements. This is what is accomplished by the process of integration. Superposition principle. Like the electric field, electric potential too satisfies the superposition principle. Suppose the electric potential at a point is V1 comma V2, comma V3, dot, 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 due to point charges Q1, comma Q2, comma Q3, dot, 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 separately, then the resultant electric potential at that point is V equal to V1 plus V2 plus V3 plus dot, dot, dot. The sum is a scalar sum, hence easier to deal with. Thus, the potential due to a collection of point charges is V1 plus V2 plus V3 plus dot, dot, dot equal to 1 by 4 pi epsilon naught Q1 by R1 plus 1 by 4 pi epsilon naught Q2 by R2 plus 1 by 4 pi epsilon naught Q3 by R3 dot, dot, dot equal to 1 by 4 pi epsilon naughts summation from I to N, where N is the total number of point charges present, Qi by Ri. In the same way as in the case with electric fields, the potentials due to continuous distributions of charges may be evaluated with usual notations. For line charge, we have potential equal to 1 by 4 pi epsilon naught integration over a line 1 by r lambda dl. For surface charge, V is equal to 1 by 4 pi epsilon naught integration over a surface 1 by r sigma dA. And for volume charge, V is equal to 1 by 4 pi epsilon naught integration 1 by r rho d tau over a volume. We may compare the formula for electric field and potential. Potential for a volume distribution of charge is this, while electric field for a volume distribution of charge is this. The unit vector r cap is absent in the potential formula, so we need not be concerned with directions while we deal with potentials. This is a delightful, comfortable situation. This brings us to the end of lesson 1 of chapter 2. We'll pick up a few more issues with electric potential in the next lesson. Till then, goodbye and thank you